and a very good afternoon to the 6th edition of the BIOCTANE webinars today about catalysis development for hydrothermal gasification. Sorry for the slight delay at the start. We had to solve some technological challenges, but I'm glad that we managed to overcome them. So I'm very happy to welcome as our guest today, David Baudouin. He's a senior scientist at the Paul Scherrer Institute in Switzerland. And as already said, he will enlighten us today about the development of catalysts for hydrothermal gasification. Why is that important for BIOCTANE? Well, within the process that is being developed in BIOCTANE, the residues from the dark fermentation will be processed at hydrothermal conditions. The rationale behind it is to allow for a full utilization of the wet organic residues, basically. And on a broader perspective, PSI is developing a broad range of catalysts, and for our project, catalysts being selective towards producing hydrogen and at the same time being stable towards coking and sintering. So give me 10 seconds for a few remaining organizational aspects, and then we can start with the presentation of David right away. And after the presentation, there will be a lot of time for questions and for discussions. So whenever you have a question, feel free to write it either in the chat or use the Q&A function of this webinar. If you would like to receive a participation certificate of this webinar, I'd like to ask you to send a short email to info@bioctane.eu. I'll put that email address also in the chat, and the recording of the webinar will be online on our website in the next few days. Having said that, welcome, David. Good to have you here. Looking forward to your presentation.
Thanks, Gunnar. So I will be, Gunnar will be sharing the slides for me as I had trouble to connect for unknown reason.
Here we go.
Very good. So I will be giving you, Gunnar already explain you what the topic of the today's presentation is. So it's about the catalytic hydrothermal gasification. So if you move to the next slide, please. So the 2 days I will be presenting you, first giving you an introduction on generally on hydrothermal treatment of wet biomass generally. Then I will zoom in and discuss about catalytic processes, hydrothermal catalytic processes, focusing on the ones developed at PSI, and then I will talk about case studies, focusing on catalyst and materials aspect. Okay, next slide, the next 2 slides. Yes, so you all know I will not teach you anything here. You all know that we have a growing demand on jet fuels and heavy-duty transport fuels also, so marine and also trucks. Despite the COVID crisis, this is expected to keep growing, and despite the limitation now in fossil fuel resources and liquid fossil fuel resources. Next slide. So the big question is, how are we going to overcome this the limitation in resources, in liquid fuel resources? So if we want to fly, flying with batteries is hardly an option, particularly for long distances. Next slide. So one alternative, it's not a solution to everything, but it's one brick into the bridge that we have to build. Is to use these huge amounts of wet biomass, wet wastes that are available and are not used or underused. And obviously the big problem to overcome with these are the low efficiency of when one want to burn biomass that contains water. Obviously the efficiency goes down as the water amount increases. And when you reach about 60 to 70%, typically you use you waste all the energy contained in the feedstock to evaporate the water. Okay, moving to the next slide. So taking as an example, one very good example of wet biomass that's available and underly used nowadays is sewage sludge. And here you find a typical and best case scenario of usage of sewage sludge, in which you would after some pre-screening and separation and sedimentation, you would apply some anaerobic digestion in order to produce biogas from the from the sewage sludge, and the digestate that is produced, the final product that you obtain from that would be then dehydrated in order to be, for instance, incinerated or used in landfills when that's available, when that's possible. And most always more countries are forbidding this. Switzerland is already forbidden since a big time. So incineration of a wet digestate is obviously a big consumption of energy and a highly inefficient step. Next slide, please. So one way to deal with, to valorize these wet biomasses is to use so-called hydrothermal processes. So here you find back the phase diagram of water, pressure versus temperature. And you see that, so you find back at the middle, the critical point of water, above which you will get supercritical water, gas and liquid on both sides. And you see that depending on the conditions applied, different products would be from different reactions, global reactions are favored. So at rather mild conditions, carbonization is favored. So that's comparable to coal production by nature over millions of years. Then there's liquefaction at higher temperature, and above the critical point, gas is formed. At very high temperature, hydrogen will be favored, while at lower temperature, methane is favored. Next slide, please. Putting this in another way, we can plot actually the treatment temperature. So we find by the temperature on this plot, but this time is the treatment time that is plotted in the x-axis. And you see that obviously as the temperature goes up, the time goes down. And you can here see the difference between anaerobic digestion, which is we count days in order to produce to have a good yield of production of biogas, which can be opposed to a few minutes in the case of gasification for the hottest processes. And it's a matter of tens of minutes for liquefaction. Next slide, please. So when we can then, of course, apply, for instance, hydrothermal gasification to a sewage sludge treatment plant, there are two approaches. Either you perform gasification from the raw sewage sludge as before it's treated in wastewater treatment plant, or it can also be applied on the digestate itself to further convert the organics present in that stream. The very big advantage in this, and I will explain that in a few minutes, is hydrothermal gasification particularly allows on one side production of gas, biogas, and on the other side it allows the recovery of phosphorus and other nutrients. Next slide, please. One thing to outline that in Switzerland, for instance, in 2026, most of the phosphorus should be recovered from sewage sludge, and this, of course, brings some challenges for the treatment plant, wastewater treatment plant in the country, and also other countries are following, like Germany. Next slide, please. Next slide, please. Yes, no, come back to the former one. Yes. So going back to the phase diagram of water, here is superimposed the solubility of salts with regard to pressure and temperature. And you see on the right is the solubility scale, and you see it's a logarithmic scale. So you can see that when the conditions get close to the critical point of water, the solubility of salts decrease extremely fast, reaching values that are in the ppm range, at least for the two salts depicted here. Next slide, please. So this, of course, on one side, it can bring a lot of trouble, as these salts, if they precipitate on the walls of a continuous process, they can clog the process, but they also could deposit on catalysts, which also would lead to trouble in this in a catalytic step of a process. So this would be the case for some salts, not all of them, fortunately. So examples will be sulfates, potassium or sodium sulfates. There will be sodium carbonate, sodium phosphate also. These salts precipitate and they are classified as a type 2 salt. Next slide, please. Now, there are all the type of salts, or the categories of salt as called type 1, which do not precipitate but form actually another phase, which is liquid, which is a brine. So it just forms a liquid-like, it's actually not technically liquid, but it's liquid-like brine, very rich in salts, leaving another fluid, liquid-like fluid, which is salt-free or salt-depleted. Next slide, please. This is actually an advantage because we can use this property to separate the salts from the mainstream. And that has the advantage to protect the catalyst from clogging. Catalysts that will be downstream this separation step. And here I show you so on the left you have very schematic scheme of a separation vessel that was designed at PSI, and on the right is a more technical one. So the concept here is the feed is fed in from the bottom, and as the feed goes up in the separation vessel, the temperature rises very quickly. And once reaching the critical point, saturation point, the salts will separate and precipitate or form a liquid brine that will fall down the bottom of the vessel by gravity, and they can be extracted continuously or semi-continuously. And at the top of the vessel, the main stream comes out and it's salt depleted. Next slide, please. Next slide. Yeah, something should have appeared in the former one, that doesn't matter. So here I show you the typical concentration or yield of gases with at a set pressure, as indicated at the bottom, as a function of temperature. And you can see that methane and CO2 dominate below 450 degrees C, and hydrogen and CO starts to increase significantly when the temperature goes up above 500, 600 degrees C. So these, of course, are for set concentration of an hypothetical composition of feedstock. These can vary, but the trend is at high temperature, hydrogen is favored, while at lower temperature, methane is favored. And if you go to the next slides, I'm outlining that the lower temperature step involve the use of a catalyst, otherwise the reaction is not fast enough for a proper industrial process. Next slide, please. So the advantage of using lower temperature with regard to higher is where we can still exploit the low solubility of the salts because we are above the critical point of water. We have the advantage to be selective toward methane, which depending on of course of the objective, it can be an advantage. It's easier to compress. Methane has this advantage above hydrogen. It's cheaper to compress. Also, it's a reasonable investment costs, as the temperature being much lower in terms of material to sustain the temperature. This is much cheaper for investing in an industrial plant. Another advantage is that the catalytic gasification can convert all the organic matter in the stream that the catalyst is exposed to, which means that all organic pollutants can be removed. Another advantage, as opposed to the higher temperature one. Next slide, please. So here I just give you. I see this is the wrong side, so you can move to the next slide. No, sorry. Come back to the former slide. Yeah, sorry. So this is just a slide introducing you with BIOCTANE and how connecting the hydrothermal gasification to the project. So the aim of BIOCTANE is to produce jet fuels using you see in the blue boxes there some biological approaches to convert feedstock, various feedstock into butanediol or acetoin that can be further catalytic converted into jet fuels. And hydrothermal gasification enters in valorizing optimizing the waste stream from the biological steps in further converting the organic matter in the waste stream into hydrogen selectively and hopefully also carboxylates. On the side, we can also, of course, produce fertilizer, as fertilizers are mostly extracted into this brine that is obtained from the salt separator that I introduced earlier. Next slide, please. So, of course, in the BIOCTANE project, I mentioned that our aim is to produce hydrogen selectively. And if you followed properly, you have seen that at lower temperature, methane is favored. So that's the challenge that we have in the project. So of course, methane will be thermodynamically favored. Now, kinetically, we can still favor hydrogen over methane. And there, of course, we have to promote some reactions versus others. So kinetically favor these before methane actually has time to form. And this is the whole point of the project into catalyst design, so that we can favor some reactions and disfavor others. So in the rest of the presentation, I will not enter into details regarding the progress on this project specifically, as it's yet too early to give you too many information. But we give you a lot of other information directly connected to the progress to the challenges of the project. Next slide, please. Next slide. So now I'm moving into describing into a bit more details the catalytic hydrothermal gasification process. So here you find back, so in a very simple scheme, you find back the description of the first steps of the process. So we have the first step of the process is to pre-treat the biomass, so it's pumpable at high pressure, and this feed can be then pumped in the salt separator that you see in the first box there. So in this step, as I mentioned earlier, salts are separated into a brine. So salts and also solids are separated. And on the other outlet of this step is the desalinated stream. So in the brine, the salts are concentrated, highly concentrated. And if you move to the next slide, so the advantage is we can concentrate phosphorus and potassium into this stream. And of course, there's a big advantage for phosphorus, particularly as the reserves are not infinite, and we're exploiting it worldwide at the moment, like it was a unlimited resource, but that's not the case. Next slide, please. So the next steps of the process would be before the catalytic conversion, we have a sulfur scavenger to protect the catalyst from sulfur contained in biomass. And then the desalinated and desulfurized stream enters the catalytic reactor, where all the biomass, all the organics present into the stream are converted into biogas. And that leaves very clean processed water, organic-free processed water. Next slide, please. So already a first word on the catalyst. I will get into much more details in the coming slides. So ruthenium is the main metal studied into this in this reaction, as it's by far the most stable and the most active. And carbon is also by far the most stable and most higher surface area support that can be used under this condition. Next slide, please. So here I list you the main deactivation mechanism that the catalyst under these conditions can suffer from. So of course you find there are lots of similarities with gas phase catalysis on other applications. So you have, of course, leaching of ruthenium or loss of ruthenium through debris of catalyst being flushed away from the bed. You have sintering, of course, Oswald ripening, different mechanism leading to loss of surface area of the metal. you have physical blockage of the metal, and of course poisoning by of the metal, of the active metal, by sulfur or other elements. Next slide, please. So the advantage, just from a process point of view, and that's why these two steps before the catalyst step were developed and optimized, is to prevent the catalyst from being exposed to salt deposition, so from clogging. So the salt separator is here for that, to remove salts and solids that could deposit on the bed, on the catalyst bed. And the next step, of course, the sulfur scavenging is a very, very important one, as biomass can contain a lot of sulfur and a very broad variety of sulfur compounds also. So the sulfur scavenger is a key aspect in the process. Next slide, please. Of course, one aspect you have seen that earlier, that methane is produced in large amounts, but also CO2 alongside. So one approach that can be followed is to co-feed hydrogen with wet biomass into the process. Next slide, please. So this was done in the group. So we co-fed. At the moment, we have only done it with model feedstock, so glycerol in this case. And so together with glycerol, hydrogen was pumped in also along the feed at high pressure. Then next slide, please. And here you can find the composition of the gas as a function of the ratio of hydrogen needed in order to convert a full conversion to convert all the feedstock into methane. Lambda 1 having 100% of the hydrogen needed to convert all the glycerol into methane. And you can see that we do not reach 100% yet, but we are getting very close to that. So that is a very good approach in order to do a power to gas process. If in the scenario where hydrogen is produced through with renewable resources, instead of stocking, compressing hydrogen, which is expensive, it can be used directly. Instead of storing hydrogen, which presents some cost, it can be directly used and converted into methane, which can be used then in the infrastructure that already exists in most countries. Next slide, please. Okay, so this I have to keep track of the time. Sorry, just yeah. So you can yeah. I do not see. Yeah. Can you still hear me?
Yes, we can.
Yes. Okay. So this is just a slide of the energy system integration platform that we have at PSI, into which we are actually, what I described earlier with co-feeding hydrogen. This platform aims at integrating different technologies so that we can overcome the problem of an excess of energy from renewable energies. So the idea with this platform is to convert the excess of electricity when we have it, to convert it in hydrogen, to store it over the season, and it can be then further converted back into electricity through fuel cells on demand when the consumption is high and the production is low. So this is the core of the platform, and we also, of course, can use the hydrogen into this for co-feeding into the hydrothermal gasification step. So we have hydrothermal gasification process integrated also to this platform through small scale units. Next slide, please. And then the one after this one also. This is a photo of the platform. Next slide. Just want to move a bit faster. Yeah, these are the two platforms that we have on the two unit that we have on the platform. Next slide. So in these two platforms, we have different TRL. So we have TRL is for technology readiness level. So we operate at 2 to 4 on one of the unit, and the other one, which is a pilot plant, we work at 5 to 6. Next slide. Next slide. Yes. So this is the small unit that we will also be using for BIOCTANE. That is used for research purposes. So we operate at 1 kilogram per hour. Next slide, please. Next slide. And this is a view. So the former one. This is the view of the pilot plant unit that was commissioned a few years ago, and this one can operate at 100 kilogram per hour. So the catalyst bed on this platform is about 20 kilograms. So it's much bigger than the scientific, the smaller scale one, which is about half a kilo. Next slide, please. Okay, I will move to the next one to save a bit of time. Next one. Okay, so now we go to case studies. So I've shown you already this slide. So I will first give you a little some information about this step, the salt separation. Next slide. On one way to optimize. So this small case study was part of another European product called HyFlex Fuel. It had similarities to the BIOCTANE, where in which we also had to produce jet fuels from different biomasses. In this case, the product was using hydrothermal liquefaction to convert the biomass into jet fuels, and hydrothermal gasification was doing the valorization of the waste stream, also aqueous phase, in order to produce more gas and to recover the nutrients. Next slide, please. Next slide. Yeah, this one. So in the salt separation into this project, we were able to at least with some of the streams tested, we were able to have a very good recovery of the salt, so extraction of the salts. You can see here the mass balance that was very high, up to 98%. Next slide, please. While the carbon on the other hand was lower. Sorry, the efficiency was lower. Of course, the aim was to have 100% of the carbon fed in, and that would be found in the synthetic natural gas produced. However, we have close to 50% of the loss in the salt separator. Next slide, please. So to make a very long story short, we performed a deep investigation, and we quantified the carbon present in the brine was up to 2/3 was composed of carboxylates, and probably more of it was also organics, not identified. Next slide, please. And we were able to optimize the process by simply increasing the temperature in the salt separator to favor decarboxylation of these organic compounds, which will lead to, of course, more CO2, but more organic matter that will not be separated along with the brine, and that will end up into the catalytic reactor, and which will be then further converted into gas. Next slide, please. Next slide. I will skip this one. Okay, so now we move to sulfur absorbance. That's directly connected to the catalyst development into this context. Next slide, please. Okay, so I mentioned sulfur. Sulfur is can be present in large amounts in biomass into a very different type of compounds. So of course there are some simple ones, H2S being the main, the most obvious one, but also COS, CS2, and of course a lot of organosulfur compounds, very, very broad variety of them. And our process have to deal with all of them. So this, and of course there are sulfates present. So now the salt separator will allow separating, removing most of the sulfate. Good thing. So some other organosulfur compounds that are charged or ionic, but there's still a big amount of them that can reach the sulfur trap. And in order to optimize the trap and its catalytic potential catalytic compound, we need to first identify them in order to better convert them and trap the sulfur. Next slide, please. So we put a good deal of effort into analyzing and identifying and quantifying the different compounds present in the stream entering the sulfur trap bed, and also the one not being trapped and not being converted and entering the catalyst bed. Next slide, please. So to do that, we did some batch tests to mimic the conditions observed in the continuous test. We also did continuous tests to confirm that the batch test was representative. So this allowed us to identify many compounds, but it's actually restricted to a few family class of compounds, which are small thiols, but also dialkyl thiols, dialkyl sulfides, dialkyl trisulfides, and thiophene, various thiophene. So these organosulfur, so we unfortunately we could only identify the volatile organosulfur compounds, which is already a large amount of work, but it's only represent a quarter of the organosulfur compounds present in the feedstocks that we studied. Next slide, please. Now, before to move into sulfur traps or materials that have some catalytic activity into desulfurizing organics, I dive in now on the big challenges of the supercritical water condition. We have catalysis into the gas phase is very well established, very well known. There are many supports that are stable and that are very well understood. Now, many of these materials are not stable in supercritical or reducing supercritical water condition. You have here in this table a good summary of the problem that we have to face often. So as many materials that are very well known in catalysis are just not usable in supercritical water condition. So we are restricted, you can see here, we are restricted to carbon, titanium oxide, some phases of titanium oxide, zirconium oxide, and a few new materials have been identified recently in our group and in other groups. It's very restricted. Next slide, please. So you found also in other studies, more theoretical, some information on the solubility, the stability regarding solubility of the material. And you can see that actually many metals are not that stable under supercritical water condition, and nickel and cobalt being having solubility issues in some conditions. So this is also adding some extra complication into designing, into identifying a catalyst for specific applications. It's restricting the field of application. Next slide, please. So I'm now moving back to the sulfur case, sulfur trap, sulfur desulfurization materials. So in this graph on the right, represented the sulfur concentration and the class of compounds found after treating the stream entering the sulfur trap bed. and the effect of different materials on these organosulfur compounds present in the inlet. And you can see that clearly that copper was identified as a very good material for desulfurizing, removing the volatile organosulfur compounds present in the stream. Next slide, please. Zinc oxide showed also some good performance. As you can, here are represented both the sulfur absorption capacity and also some information regarding the physical stability under the conditions applied. So while copper oxide has a good absorption capacity and desulfurization capacity, zinc oxide also have good ones, but their stability is limited. While serum oxide, on the other hand, showed very good stability, excellent stability, and reasonably good sulfur absorption. So there are pros and cons in all cases, but that led us to identify serum oxide as a good potential material for further development. Next slide, please. So now we move away from sulfur. Move to now focus on lithium-based catalyst. Next slide, please. Yeah, so this is, we move to next slide. Next slide, please. I already mentioned to you that lithium is the most active metal under these conditions. And the big question is what is the active phase in this catalyst? So when we start lithium is exposed to, of course, the conditions are reductive, but there's a large excess of water. So this, for a long time, the active phase was believed to be lithium oxide. It turned out by doing in situ X-ray absorption spectroscopy study, you can see on the right that there is a direct proof that the lithium gets reduced very easily as early as 150 degrees C. It gets reduced to lithium 0. So this was a direct proof that lithium 0 is the active phase actually under these conditions. Next slide, please. Next slide. Okay. In all the presentation, in the rest of the presentations, I will focus on lithium supported on carbon nanofibers. So often activated carbon is used because it is much cheaper. It also has a high surface area, but unfortunately, activated carbon is mostly macropores, and these are actually completely useless under these conditions because they get filled very easily, and lithium is mostly not present in the macropores, but in the mesopores of the activated carbon. So carbon nanofiber is used in most of our studies, scientific studies, in order to largely simplify the study of the catalyst, of the spent catalyst. Now you have example here on the, yeah, thanks for next slide, perfect. We studied the catalyst on a small lab setup, continuous setup with a fixed bed reactor filled with this lithium on carbon nanofiber. And the gas is analyzed online, and the process water analyzed for the remaining unconverted organic compounds. Next slide, please. So here you find typical results obtained from the test done on this lab scale setup. So we find on one side the gas composition, of course, and the gasification efficiency, so the quantity of carbon found into the gas phase with regard to the amount of organics fed in, and also there is the conversion of the organics present in the feedstock. Next slide, please. Okay, one study that we did was to look at the effect of particle size on the catalyst performance under these conditions. This has been an open question for quite some time, and here I report a long study into just a few slides, a few graphs. So you find here, based on the using many tests that we did on the setup that I introduced the slide before, we came up with this graph, which represents the turnover frequency of the catalyst. So the initial one, at least at the first 30 minutes, as a function of the particle size, initial particle size. And you can see that there is no clear particle size effect unless you go to close to 1 nanometer size, where the activity seems to increase dramatically. Next slide, please. Now, the catalysts suffer, however, from deactivation, or very, very early deactivation, and then the catalyst finds some stable activity. And here is reported in red, the turnover frequency after stabilization. This, of course, is updated with the dispersion of the metal after the test. And you can see that there is no much correlation observable anymore with particles at 2 nanometer with having very different actually turnover frequency. Next slide, please. Now it turned out that we have observed that there were some signs that the loading had some effect on the performance of the catalyst, and that we are further investigating that. And actually, by plotting the turnover frequency with regard to the surface loading of ruthenium, we find out the same correlation for turnover frequency, the initial turnover frequency, but we find also some correlation that actually makes sense with the stabilized turnover frequency. And it seems that there is an optimal surface loading of ruthenium that was found for CNF, but also for activated carbon. Next slide, please. So of course, this raises the question on where this what is this caused by. So there are indications that the surface plays a role also in the activation, and actually the clean, free surface that is free of ruthenium particles might play a role in the activation of the catalyst. So this is something that we have, and of course by this I mean the deposition of coke, and this is something we have further investigated. Next slide, please. So I'll come back to the slide that you have seen before, the different mechanisms that can explain the deactivation. So before to move to the question of coking, next slide, please. I just give you a few hints regarding leaching. Next slide, please. So the loss of active metal from our catalyst bed. Next slide. So we use the same setup that I introduced before. We used ICP MS and not OES, for the MS being much more sensitive than OES detector. Next slide, please. And we're able to test the loss and the leaching or loss of metal from the fixed bed at different conditions, so different temperatures, different feed concentration, because we know that now that feed concentration has a big impact also on leaching on some metals. And we observed that there were no big difference, no effect of these conditions, at least the ones that we applied on leaching, which remain extremely small. You can see that the units here, we are talking about microgram per liter of ruthenium. And this is close to the thermodynamic value calculated and that can be found in literature. Next slide, please. However, we found a huge impact on the pressure on the process condition. So when the process is very smooth with no fast change of pressure or change of temperature, there is very, very low leaching of ruthenium. And you find here an example of after 250 hours on stream in the frit that is downstream the reactor that's protecting the back pressure regulator. We found a very small amount, 29 nanogram of ruthenium. And after 4 hours of a test with on purpose abrupt changes of pressure, not that abrupt, but changes that can be observed during process from different reasons, from leaking or from uncontrolled sampling, for instance. We observed that there was a very large amount of ruthenium just in the fruit, and also very large, much higher amounts into the processed water obtained downstream. Next slide, please. So next slide. So that was a conclusion. We identified conditions that should not be applied. A process condition should not be reached in order to avoid damage of the catalyst beds, particularly on large scale. Okay, next slide, please. So I'm now moving to the coke that I mentioned earlier. So the deposition of deactivation due to carbon deposition or coke deposition. So first is, what is coke? In the gas phase, you probably have seen that reforming. It's very well known in reforming. Coke deposition occurs through layers, and that in the worst case scenario can end up to formation of carbon whiskers that are actually the way to produce carbon nanofiber that I presented earlier. So you have a good example on the right with these layers being formed on this example on ruthenium. By the way, this is very particle size dependent. This occurs only above 4 to 5 nanometer particles and not below. Now, in a supercritical water condition, if you come back to the former slides, on the left, the deposition that we observed was very different. Seems to be much more homogeneous and much more amorphous. We never observed the formation of this type of layers that you see on the right. Next slide, please. So moving back to the setup that I presented earlier, we perform different tests at different conditions. So we perform tests on the thermodynamic conditions, so full conversion of the feedstock. We've also performed on the kinetic regime, so below 20% of the thermodynamic regime, and also some intermediate conditions. And we collected the catalyst, the spent catalyst, and we extracted the organic matter that deposited on the catalyst bed. So this extraction was done with a mix of solvent that is very efficient into dissolving heavy carbons and particularly aromatic carbons. And these extracts were analyzed by HPLC HRMS. Next slide, please. So again, to make a very long story short, this is one set of data that were obtained from this study. You can see here on the top, you can see the double bond equivalent as a function of the molecular weight of all the compounds, all the peaks that were identified in HPLC HRMS, and there are many of them. So you can see that there are a lot of double bond equivalents. So by double bond equivalent, I mean some double or triple bonds, but also the presence of oxygenated functions. And right, I will not comment the bottom one. So next slide, please. On the right, so I'll come back to the former, this one. So on the left, the top left, that I presented already, that was what was observed after catalyst exposed to intermediate reactions. So all the organics were not converted, but most of them were converted. And the one on the right are the extracts obtained after a test done at the kinetic regime. So only 20% of the organics were converted. And you see that there is a huge difference first in the molecular weight of the deposits, but also in the double bond equivalent. It's a bit higher, but overall it's not so far from it. They are generally more, particularly considering that the molecular weight is lower. Next slide, please. Again, making a very long story short, we were able to identify a mechanism, a reaction pathway, that yields to the formation of aromatics that deposits on the catalyst. And we identified aldol condensation, which are the step 2 to 3. And at this aldol reaction, which is step 4 to 5, as the core steps in order that yield to aromatics to aromatics and polyaromatics. You have a good example on the right of one compound that was present in high concentration, and that it's a starting point for formation of more larger polycyclic aromatics. It's important to stress that dehydrogenation occurs only in ruthenium, and that was not observed on the support itself. Next slide, please. And I'm coming to an end. So in short, I hope I'm convinced you that hydrothermal of the good potential and nice potential of hydrothermal processes in general, gasification in particular. But also I have outlined some challenges that are faced with regard to developing catalysts in this field. Now, ruthenium on carbon is a star for when it comes to the production of methane. When it comes to production of H2, that's there will be a lot published in the coming years from us, hopefully, for the selective production of hydrogen. And we have to shift away from ruthenium, which is too selective towards methane. And some of the strategies that we follow are poisoning it, selectively poisoning or doping it, and using different new supports. And next slide, please. I would thank you for your attention, and I also thank all the group members and all the partners in our group that were big contributors to the slides that I showed you today. And thank you for your attention.
Thank you very much, David, and thank you for this broad and simultaneously in-depth overview, not only on catalysts for BIOCTANE, but more on catalysts in general. We have received one or two questions. So the first one is, I suppose, rather to the end of your presentation. What's the temperature range at which glycerol dehydrogenation takes place over ruthenium?
So this is typically met at 400 degrees C, at least that the conditions we applied. So I can 100% tell you that it's happening at 400 degrees C, and the reaction pathway that I introduced is occurring at this temperature. Now, part of it, so the first steps, are also observed without catalyst, glycerol alone in supercritical water, or in near critical water. So I think at 350. The steps are already occurring.
Okay, thank you. And then a slightly broader perspective. So you mentioned that you want to prevent methane formation in order to promote hydrogen production. And if so, why did you feed hydrogen into your process? I suppose it's two different processes, or is there a rationale behind it?
Yeah, these were different approaches. BIOCTANE is one thing, and the aim is to produce hydrogen. And the example where hydrogen was co-fed to produce more methane, that was another scenario. Hydrothermal processes, like all processes, have to adapt to the consumer in the end.
Obviously, okay. Thank you. That definitely makes sense. Two different processes and projects, presumably. Could you elaborate a bit on the use of glycerol? I think on several points you mentioned that you usually use glycerol as a first try solution. So what are advantages and disadvantages of using it?
Yeah, good question. So there are many reasons. The main ones are that it's a compound already easily found in nature, in biomass feedstock that we use. It has the chemical functions that also broadly present in biomass. Its molecular formula is close to an average for biomass. The carbon-hydrogen to oxygen ratio is rather close to a representative of the biomass that we typically have to deal with. So these are the main reasons. Other good reason is it does not coke that easily. And it does form coke alone, without catalyst in supercritical water, but not that it's not nothing critical. So it also makes it a good model compound for that reason.
Okay, thank you very much. And I had a question at the beginning of your presentation, since you mentioned there are a few treatment steps required, like the removal of salts, the removal of sulfur, etc. Could you elaborate a bit on the energy requirements for those process steps compared to, for example, the hydrothermal gasification later on?
Well, all this is done, the whole process have to be seen as a whole. Actually, the main energy input is at the point of the salt separator. That's where all the energy in external energy input is on a large scale process.
Mm-hmm.
Now, a big part of the energy is recovered. That's also the beauty of hydrothermal processes. The energy recovery is very high, thanks to the phase that's used, and it's water. So we in our pilot plant, I think we were able to reach close to 85% energy recovery, which is pretty good. And the missing 15% and the extra energy input is at the salt separator, so that I could not really comment one step versus the other in terms of energy consumption, as they are linked with each other.
Understood. Yeah. Okay. Thank you very much. That seems to me like all the questions that we've received and that came up in my mind. So unless there are any further questions, I would like to take the remaining minute to say thank you to you, David. I think that was really an insightful and important aspect of our project, so more or less the missing puzzle piece for our webinar series. So thank you very much for taking the time and for joining us today. As I said, for those who would like to receive a participation certificate, just send us an email to info@bioctane.eu. You can now find the email address also in the chat. And yeah, stay tuned for more updates on our project. You might have read that we are currently organizing a scientific workshop. The program is already out and there will be more infos coming soon. So looking forward towards meeting you on one of the next either BIOCTANE meetings or in October on the scientific workshop. Having said that, thank you very much, David. Thank you all for listening in and see you soon. Bye.
Thank you, everybody. Bye.